All right, welcome to part 2 of our population lab. We are talking about population growth. So the rate of natural increase depends on two things: the number of individuals born and the number of individuals who die. So in humans, in this example, about 20 births per 1,000 people each year. About 8 deaths per 1,000 people each year. So what that means is more people are being born than are dying every year. So this was, I can't remember when this data came through, 2000 something. Pre-COVID, that's for sure. So our birth rate exceeds our death rate, which means our population is growing. So let's even simplify it more. There are 100 people in a population. Over the course of a year, 20 babies are born, 8 people die. The new population is 112, right? So you had 100 people in a population, 20 babies are born, so that makes it 120, but 8 people die. So we subtract 8, so the new population is 112. So we're growing. We have what we call mortality patterns. So a cohort, I know it's a lot of definitions. A cohort is composed of all of the members of a population that are born at the same time. Okay. Survivorship is the probability that newborn individuals of a cohort are going to survive to a particular age. So let's say a fish laid 200 eggs, because they do. They lay a ton of eggs. All of those eggs would be a cohort. So how many of those newborn individuals are going to survive to a particular age? And that gives us survivorship curves. So there are 3 different types of survivorship curves. Here we have age, so increasing, so 0 when you're born, all the way to whatever age. Number of survivors. Okay, so we all kind of start out here. We're all born, so 1,000 babies are born. And then a bunch of them die. Okay, these are the number of survivors. So these are the number that survive to what? Let's say age 5. So most of the individuals in these type species die before they even hit 5 years old. Okay, but once they kind of hit that golden age, they tend to last. They tend to stay for a long, long time. So this involves most types of fishes, invertebrates, insects, and plants. So think about what I was saying, the fish that lay so many eggs because so many of them get eaten. Plants make so many seeds because so many seeds either get eaten or don't fall on good soil, and so not many survive. Okay, that kind of makes sense, right? There are many birds and mammals that just kind of have this even curve. They just kind of, they don't super die young. They don't super die old. They kind of just have a gradual decline in survivorship. Humans, other large vertebrates, when typically babies survive. This is, post-industrial world. We've got good health care, whatnot. Most babies survive. And we tend to survive. You get really surprised if someone dies young, right? You don't seem so surprised when someone's 70, 80, 90 years old and they pass away. We kind of, as humans, tend to all survive, or the majority survive, until we get old. And then when we get old, it's just crash and burn. We have what we call R strategists and J strategists, right? Okay, I was close. Okay, our strategists are opportunistic species. They produce large numbers of offspring, typically have a small body size. They mature early, tend to have a short lifespan. They don't invest a lot of energy in parental care. They tend to be good dispersers and colonizers. So, can you think of some species like this? We talked about fish, a lot of fish. Mice are a really good one. They produce large numbers of offspring compared to their body size. So mice mature within just a few short weeks. They can start having litters, and they can have like 15 mice per litter. And they can have a litter like every 2 weeks or something crazy. They're small body size. Mice only live about a year or two. They kind of help their offspring to be able to fend for themselves, and they're gone. They're good dispersers. They colonize everywhere. So they would be good R strategists. K strategists are equilibrium type species. So humans. All right. Produce smaller numbers of offspring. Have a large body size. They mature later. They have a longer lifespan. They invest a lot of energy in parental care. Tend to be strong competitors. Often very specialist. So humans, bears. Let's go with bears. They typically have 1 to 2 offspring at a time. Larger body size. Takes them several years to mature. They can live 30, 40 years. They invest energy in parental care, so their cubs will live with them for 1 or 2 years. Strong competitors, and can be specialists. So what happens when a population grows too large? They can suffer from starvation because they've eaten up their own food supply. So for example, deer hunting was banned on Long Island, New York, and the deer population exploded. They quickly outgrew available food resources and ended up starving. So basically there was no grass, and the fawns, they were the first to starve because they couldn't reach higher in the branches. So you had a decrease in population because of that. Age distribution. So a lot of these concepts are going to be coming up on your simulations. Age distribution. This is the proportion of the population that falls into various age categories. And there are 3 major age groups. Pre-reproductive, so child. Reproductive, the age that you can reproduce. And post-reproductive, which is no longer able to reproduce. And not many animals actually live to this point in the wild. Humans do, but not very many animals make it to the point where they can no longer reproduce. Oh, there's a typo there. I need to fix that. There are at least 3 age structure diagrams possible. Increasing, stable, and decreasing. So we're going to show you those. Here we have an increasing population. Okay, you have a lot more children than you have reproductive and post-reproductive. Okay, here's males, here's females. Stable population is you've got about the same number of children as you do reproducing adults. And you're always going to tend to have less and less of the older ages. Decreasing population is when you have less children than you do reproducing. Okay, so this population is going to decrease. And right now in the world, the human population is experiencing exponential growth. The doubling time of the human population is estimated at 52 years. So every 52 years, we are doubling the amount of people on the planet. In 1800, we estimate we had about 1 billion. By 1930, we had 2 billion. 1960, 3 billion. 2000, we had 6 billion. And that's the last bit of data I have from that. Now, if we look at more developed versus less developed countries, less developed includes a lot of Latin America, Africa, Asia. They are experiencing rapid population growth. They also have a low standard of living in many places, typically rural. And their strategies are to reduce population growth. So China was actually growing so rapidly that they instituted rewards to families that only had one child. And there were like financial consequences and whatnot if you had more than one child. So the strategies, family planning programs, social progress, which might reduce the desire for large families, delay the onset of childbearing, things like that. So young marriages, farming communities where the more children you have, the more help you have on the farm. Those are reasons why you would have larger families. But we're trying to kind of curb this growth. Now, in more developed countries, North America, Europe, Japan, Australia, we have slower population growth. We tend to have a higher standard of living compared to those underdeveloped countries. A demographic transition occurred. Decreased death rate, followed by decreased birth rate. So we got better medical care, so we aren't having as many people die. We're also having less people born, so our population growth is kind of stabilized. A century and a half ago, U.S. tended to have large families for many reasons. Early marriages, lack of birth control, free labor for the farm. But now that we're more developed, we are seeing later marriages, later families being started, and not as many. You don't hear about many 1 of 11 siblings anymore, except for maybe your grandparents. So here we have more developed countries, population growth, and this is estimated, this is predicting, while less developed countries are having exponential growth. So if we want to not hit our carrying capacity and have people begin starving on a massive scale, we need to curb a lot of this population growth. So you're going to look at some of that with your simulations homeworks this week. Again, if you run into any troubles, any questions, email me. I'm happy to go over things with you. All right, and I will see you next week at our regular Zoom time.